So let's now look at an example of how we can perform a chi-square test to test for goodness of fit. And this lesson in this video is highly recommended to be watched after you have viewed or watched my other video lesson on the general discussion or general lecture about how to perform a chi-square test for goodness of fit. Because here in this lesson I am going to pick up the pace for the steps. Alright, so let's spend some time reading the wording of the example here. So at start, a sample was selected and showed the counts for 4 population categories as described in a given table. So let me quickly now bring up the given table. So in this table here, what we have here is a sample. And the total of this sample is 50. And so how I see that here is that, and here we don't even have to worry about what these categories are. There are just some categories as explained in the general discussion, that any population can be divided into some number of categories of concerns, of interest. And so in this particular sample, we observe that there are 12 members from this sample. It could be 12 people, it could be 12 individuals, but in this sample there are 12 that belong to category A. There are 22 from this sample that belong to category B, and 6 for category C, and 10 is for category D, and so on and so on. And again, we put ourselves in the assumption that for any of these members in the sample, once it has already stayed in one category, it won't stay in any of the other categories outside of the category it's already stayed. So any member only stays in one category. And so that is the column that lists all of the observed counts that we found in a sample as described in the problem. So now let's continue reading it further. So it is claimed that the population proportions of the 4 categories in the table are equal to one another. And so let me quickly highlight that term right there. So that means this is a good clue for us to know what the claim is. In this particular study, we only study about 4 particular categories: category A, category B, category C, and so on, and with D here. So with only 4 categories here, and it was claimed, again, it was claimed that the population proportions of the 4 categories in the table are equal to one another. That means lowercase letter p with the subscript A is to represent the population proportion for those in the population that falls in category A. So that population proportion must equal the population proportion of B, of category B. So that's what the P with the subscript A and P with the subscript B. And that also equals the population proportion of category C. And the same with the population proportion for category D, because we have 4 separate categories. But so as a further impact, if all of these 4 population proportions are equal to one another, then that means each of these has to all equal 0.25, because we have 4 different categories and they are equally divided in the population. So that means each of these gets a proportion of 25%, or in decimal 0.25. So now we can easily come back to our table and write the claim as the following. So in the population, it is now claimed that 25% is for category A, another 25% is for category B, another 25% for category C, and of course another 25% for category D. So all of these proportions are equal. So again, the reason I know that it has to be 0.45 because all of these will add up and being 1 or 100%, which is the total in the population, and they're all equal, and that's the only way. And so now, after having some understanding about the data and the description of the problem, then the question is brought to us here: at significance level 0.001 is the sample showing strong evidence that not all population proportions claimed are correct. Or in another way of saying it, as how I explained back in a general lecture, then the same question here can be stated as, at significance level 0.01 is a sample showing strong evidence to reject the claim about the population proportions. The claim here again is that all of these proportions are equal to each other, and specifically equal as given here, 0.25 for each, because there are 4 proportions and they're all equal. So now that means in our hypotheses, we can write down the 2 hypotheses as following. H1 can say that not all population proportions are correct. That means it could be some of them in the list here being incorrect. Then now H sub 0 can be saying that, can be a statement saying that all population proportions are correct. And so now, assuming that anyone viewing this video has already watched my earlier video lesson or have had some understanding about how to do a chi-square test for goodness of fit, then let me allow me to pick up the pace here as I'm going through the steps here in this particular lesson. So now let's have a look closely at our table one more time before I'm completely getting into the steps, so that I won't have to switch back and forth between my writing board and this table on the computer screen anymore. So these are the proportions, the population proportions being claimed, and we're trying to prove that not all of these are correct, meaning some of these guys must be incorrect. And then these are our observed counts in the different categories here. And so the first step now is to be finding out all expected counts. So for category A, and allow me to write cat A, that stands for category A. So the expected count there is expected that, and we can call that, this is category 1. In the sample of 50, if that proportion stated there being 25 is truthful, then I expect that for that category, I expect that there should be 12.5 after multiplying 50 and 0.25. The same for category B, or namely in this category, namely category 2, I expect that, and as expected count E2, that in my sample of 50, in the way that 0.25 is accepted to be truthful, then I expect that there are 50 times 0.25, which is 12.5, as the count expected for category B. Again, if that population proportion was true. Then for category C, namely third category or category 3, in a sample of 50, if the population proportion for category C truly was 0.25, then I expect that, so multiplying these will give the expected count. I expected that the count expectedly for category 3 must be, again, another 12.5. 0.5. And for the last category, category D, namely fourth category or category 4. Again, if 0.25 is truthfully the population proportion for category D, then in a sample of 50, multiplying these, it gives me the count I expect for category 4. So E4 equals 50. The total sample size multiplied with the population proportion designated for this particular category. And the answer again comes out 12.5. And so that's how I have recorded all of my expected counts in this third column in the table that's labeled here expected. So this column is where I recorded down all of my expected counts that I have calculated previously from my writing board. And now after getting all of the expected counts done, the next step is to calculate. So I'm going to be saying the next step is to be calculating the components. And so again, let's have a quick observation of our table. So for category A or category 1, I expect in this sample to have 12.5 of them in this sample being in category A. However, it shows as observed count only 12. Similarly, for category B, I expect in this sample to have 12.5 if the population proportion for category B really was 0.25 as indicated here. So that's my expected count recorded here, but the observed count actually turned out being 22, and so on and so on. For category C, in a sample of 50, I expect 12.5, but observed count really showed only 6. And for category D, in my sample of 50 members, I expect 12.5 as a count to be for category D, but it showed only 10. So in any of these categories, there has been a difference, either small or large, between expected count and observed count, expected count and observed count. And sometimes, again, in what I explained in the general lecture, the difference between observed count and expected count can also be 0 in some cases. And so that's the reason why we are calculating components to be the next step. And so now back on my writing board, components for category 1, namely category A. The observed count there was 12. And now I'm going to subtract the expected count being 12.5, square the difference, and divide it by 12.5. And so I need to remind anyone that components at any ith category can be found by observed count minus expected count of the same category. Then square the difference and divide that square by the expected count of the same category. So here, when we're at particularly category 1, the components there is 12 minus 12.5 in parentheses squared divided by 12.5. Calculation of mine show 0.02. And as I have discussed in the general lecture and throughout all of my video lessons regarding performing a chi-square test for goodness of fits, I will round all of these component values to 2 decimal places unless being specified otherwise. And again, I leave that responsibility for viewers and students of mine to watch for any rounding requirements in each of your problems that you're doing. And so here, component value is rounded to 2 decimal places. So that's how it arrived at 0.02. Then now we're heading out to the component value for category 2. And according to the table, observed count there was 22. Now I'm going to subtract 12.5 being the expected count. Square the difference and divide it by 12.5. My final calculation for this in 2 decimal places, 7.22. And now we can head out for third component, namely or symbolically comp3. In the third category, according to the table, we had 6 for observed count. I'm going to subtract 12.5 for the expected count. The difference there is going to be squared and divided by 12.5, the expected count again. Calculation showed 3.38 in 2 decimal places. Now for our last component, the table of mine showed 10 for the observed count. From there I'm going to subtract 12.5 as the expected count in the same category. And I'm going to square that and divide it by 12.5. Calculation of mine showed 0.5 as the components for this. And now I recorded all of my component values in the fourth column here of our current table. And so now, after getting all components calculated, our next step now is to calculate the chi-square value. So now we're going to be calculating chi-square. And again, just as a reminder, any chi-square is just simply found by the sum of all components. So in that way, my chi-square, specifically in this case, is going to be according to what I have recorded, all of my components here. Then first component was a 0.02. I am going to add to it another 7.22 for the components in category 2. I am going to add to 3.38 as the components for category 3, and I am going to also add with 0.5 as the component value for category 4. So now chi-square is going to be the total of all these 4 component values. So final calculation came out to be 11.12. And so now at this point along the way, we can see that in this problem we're working with 4 categories. And so the degrees of freedom of our problem will be the number of categories 4 minus 1. And so the degrees of the overall degrees of freedom for our problem here is 3. And now the next step is to calculate the final p-value for our sample based on the chi-square value that we have already observed here. So calculation setup for p-value is done as following. We're finding the probability where among infinitely many chi-square values, we're going to find a chi-square greater than or equal 11.12. So again, always a right tail inequality here, and the value here in our inequality comes straight out from our chi-square that we have calculated previously. So now on my calculator and throughout my entire lesson here, I am going to be using the TI 83 and 84 calculator. So I'm going to go second variables to bring up all of my distribution functions in statistics. Scroll down to option number 8 here on the screen that says a chi-square CDF. Hit enter. So the lower end of our interval here is that designated 11.12. My upper end, according to what it says here in the way how this interval looks, then the upper end is an indefinite operand because we want to be anywhere greater than or equal 11.12. So in that way, I am going to leave 1e99 for my operand. And again, for anyone who is unclear how to get 1e99, 1 second, comma, that's for e99. We're working with degrees of freedom 3, so that's what it is. We don't need to change that. Now I'm going to hit enter a few more times. Ready for executing it. Now, in case you have a TI-83 calculator or some of the earlier TI-84 calculators, then your chi-square CDF command will be, instead of a menu, printed directly on screen as seen here. So to enter your interval, low n is going to need to be typed in first, 11.12, then a comma, then we're going to go 1 E99, and with a comma, and now degrees of freedom 3. And we complete our command by hitting a closing parentheses. And now let's find out what the final p-value is by running this command right here, by executing this command. And so now our final p-value looks as following: 0.011094378, and supposedly a lot longer. So in this case, right out from the value that came out from the calculator, I'm going to round that to 4 decimal places because this is my final answer. So 0.0111. So this is our final p-value. And as I have explained so many times, anytime it comes down to p-value, unless being specified otherwise, I will round that to 4 decimal places for my final p-value. But I leave that responsibility for students and viewers to watch closely for rounding requirements in any of the problems that you are doing. And so now the next step is to compare our final calculated p-value with the significance level given in the problem. We want to find out whether our p-value is below or above the given significance level. And that's what needs to be addressed. So now back to the wording of the question itself here. Then right at the beginning it stated that at significance level at alpha equals 0.001. So what it means now is that we already had a given significance level. So that means now my final p-value must be compared with 0.001. And now direct comparison shows that our final p-value is still above the given significance level. So in this case right here, in the understanding about testing any hypothesis, anytime we come to the final value, we have come to the final value being above the given significant level, then we can say that nothing unlikely about the sample. Or another way of saying, the sample we had here is not an unlikely sample. And so then in that way it leads to a further decision that the sample is not strong evidence or not showing strong evidence. Not strong enough for us to reject H sub 0 or to support H1. And ultimately, the question itself is a yes or no question. As stated here, is the sample showing strong evidence? We apparently show that we did not have strong evidence. So in this case here, really it means we fail to reject. We failed to reject H sub 0. And the same as we fail the same as saying that we failed to support H1, all due to the fact that we don't have strong evidence. And so back to the ultimate question. Now our answer here is no. So even if any of our observed counts here makes some difference with the expected count, but in the end the chi-square value, which led to the final p-value, is still indicating that in a way how our sample looks, it's still nothing unlikely compared to the acceptance about all population proportions are correct. So that's why in that way we fail to reject H sub 0. So that means there's still a likeliness that all values claimed, all population proportion values claimed in our H sub 0 statements can still be correct somehow.